almost looks like that we're making a case that we really do believe there are pods out there that you can drill and get additional reserves. And when we do the history matching and look at all the data, there is no aerial heterogeneity that affects reservoir performance at all. And this is particularly true for gas. You got to go almost to zero permeability not to be able to move gas because of its viscosity being so low. But we worked with the geologists and the log analysts, so and so, and we were able to convince them by looking at data. You know, how can you have layers out there still at 300 pounds while the original was 400, and you have the Kreider and the Winfield layers at 100 pounds? How can this exist? Boy, you have to have absolute zero crossflow vertically. And we looked at out on the edges, the east. With east flank and the west flank, we looked at replacement wells that were drilled, and I'd mentioned to you earlier that sections that had as many as 4 replacement wells drilled, and maybe 10, 15, or 20 years between 2 of them, and you have over a 200-pound depletion in pressure without any production coming from that well on that section. You have to be being drained by the offset, so everything was being drained, regardless how much it varies aerially. This is a schematic. I don't think this is in your notes anymore. Okay, I've got the overheads here. Some of this is going to be in your notes. This is some of the detail. I had to shorten this presentation when I normally get it because I usually combine both the rate time and also the layering at the same time. But this is a schematic of the Phillips acreage and the Oklahoma Hugoton. This is the Texas-Oklahoma line here, and this is the Oklahoma-Kansas line. Well, the green colored area here is a Phillips acreage. The geologists and log analysts ran some cross sections east to west and north to south. Normally, in a region, or they'd follow a path where there are a lot of deep wells drilled in this region. So we picked a lot of areas because the deep wells had modern logs available on them. A lot of these other wells were drilled in 1945, and they virtually didn't run any the modern suites of logs. So if we're going to do our work, we need something reasonable. And this is the region that we picked for our 12-section model study, about in the center of our acreage, plus the 12 sections, plus the sections all the way around had deep wells drilled on them. So we had logs available on all of the sections. So we went one section on either side, too. You get to do the correlation. With correlation work with regard to layering and so on and so forth. This is the end, approximately, the Texas Hugoton field. We'll get into that just a little bit. And then this dividing line, you get into the West Panhandle, which is also about the same age, and it's one giant reservoir where the oil rim has produced well over a couple billion barrels of oil, and the gas in place between the West Panhandle and the Hugotons into Kansas was over 70 trillion cubic feet. And I remember one day I tested a well down in the East Panhandle, and I had to test one up over at the Kansas line. I had to drive 250 miles. You get to test, you have to get a couple wells off test in the same day. It's that big. I don't know if this is going to show up on with the camera, but this is a little more descriptive of the 12-section study area. This is the region we studied with a model, but we also utilized data from a section all the way around. And we also took a look at things being dominated primarily by the more permeable layer. We took a look at the flow rates between wells on either side to make sure that the no-flow boundary was very close to the 12-section study area. I think it was about 1% off in total volume. So that, you know, the very first thing you're going to ask, or anybody's going to ask, is, yeah, but if one well is no good, why is 12 good? Why shouldn't you study the whole field? It'd be impossible. But we did take a look at the no-flow boundaries by proportioning producing rates of offset wells, and it approximately confined it to the 12th section. This is a north-south cross-section from Texas-Oklahoma line here, and we went clear up in across the Oklahoma-Kansas line because we want to establish how much different is the reservoir in Kansas than it is in Oklahoma, because, you know, the infill drilling was approved there, and we want to see if we could apply the results they got there into Oklahoma. And then, of course, we knew that if we did go to hearing and we lost in Oklahoma, we're going to have to go into Texas next, and then in the West Panhandle, and then in the Permian Basin, and then the Gulf Coast, and there was no end to it. This is why we got involved. And the structure goes up into Kansas, so that layers in Oklahoma. The Phillips acreage is down in through here. Okay, there's approximately the Phillips acreage. And as you can see, when we get down into our part, the Harrington, the Crider, and a little wee bit of the Winfield has got gas, about 5 feet. Every well that we drilled, we tried to make a completion in the Winfield. We perforated, did a light acid wash. Now, if we get dry gas, we'd complete it. Ordinarily, when you acidize in there, you usually got water also, so we plugged it. But in our 12-section study area, 3 of the 12 wells were originally completed in the Winfield. When you get into Kansas, again, some of these layers, like the Winfield, is completely dry here, and then you get into the Fort Riley. What also happened in Kansas is the Harrington up there, they never even perforated. They didn't consider it pay. But the Fort Riley turned out to be their low perm layer. You know, so they had their low perm layer on the bottom, and we had our low perm layer on the top, which is the Harrington here. The Crider is a good quality reservoir rock clear across the Texas, Oklahoma, Kansas, and even when you go down into West Panhandle, they refer to it down there as the brown dolomite, which is also the best quality reservoir rock. And when you look at all these wells, remember, what would you have done in 1945 when you had maybe a dozen wells drilled in a confined area, and this covers about 30 to 40 miles wide and about 50 miles long, and you've only got a few wells? How are you going to assume that this shale that now we have them all drilled and we can correlate them on logs was continuous everywhere? You say, well, since I don't have that, I'm not going to assume it. Since I don't have that information, when are you ever going to have that information except after it's all drilled and developed? Now, this is why, in my opinion, you're obligated to make the assumption I'm going to forecast this reservoir with the assumption of no crossflow also, and see how bad it is. It's not necessarily a disaster. Remember, it's the ratio of those two. It might turn out that it isn't going to make any difference, but as a reservoir engineer, I think you're obligated, particularly when you start to get involved and say, I'm going to improve my work because I'm going to do this very sophisticated risk analysis approach to reservoir engineering. Well, the risk is that it is no crossflow. That's the risk. And as you begin to study more and more reservoir performance, you find out that the majority of reservoirs are no crossflow. There's no crossflow. You can see that these shale barriers, you can correlate them across the whole field, all the way into Texas, Oklahoma, and Kansas. And this is an east-west cross-section. You have the Oklahoma Hugoton field. You see we've got the Harrington, the Crider, and a little bit of gas in the Winfield. And I think there's an elevation difference here of about 900 feet. And as you move in this direction, you move towards where the rocks start to get a lot of clastics in it, the quality of the reservoir starts to drop off. You know. In through here, it's primarily carbonate or essentially dolomite. And when you go back and look at the some of the testimony in Kansas, the geologists, in my opinion, were impartial in trying to do their work technically sound. You can see the same type of layering, and you see these black shell streaks that correlate across the entire field. You know, when you talk to geologists, say this should be expected for carbonates. You know, it's a blanket deposition. You're cyclical. You always don't have the good limestone. You have some of the mudstones too in between. And again, 45 years, 300 pounds in one layer, 100 in the other. There is no crossflow. Zero. It's not small. It's zero. There's a difference. You have to remember, at one stage in reservoir simulation, everybody automatically used the number of 0.1 is the crossflow factor. And originally it was done to keep it numerically stable. When we took our gas model and tried to run it as a layered no crossflow, it blew up. It wouldn't run. It couldn't handle backflow. Yeah, so you're creating numerical instabilities when you start to run these types of problems. So I don't know if that was a part of what the problem was or not, but we could not run the model in a layered no crossflow mode. It couldn't handle the backflow. And you can see how you can also get into a problem with a multi-phase system, you know, oil. So I'm sympathetic there, but you ought to set up some runs with the gas and make some runs and kind of you play with it a little bit and find out what's going on and how you can simulate the shut-in pressure. And the shut-in pressure you're getting represents that of the more permeable layer, nothing else. And you can't extrapolate it. And this is nothing more than the east-west cross-section, or no, the north. Looks like it's north-south on that one. Yeah, this is the north-south cross-section in Kansas. Well, they got one here. They show a little bit of a window, but you think, are you well over here is going to see that window? It's amazing what happens when you change a parameter in one well, in one layer, how it affects everything, everywhere all of a sudden. That was a big surprise, too, because everything redistributes itself. Okay, here's an example of layer pressures that were obtained in Kansas by Mesa, Pickens. They're all for infill drilling, and they're all for getting a double allowable because they really need the gas, really need the money right now. But up in Kansas, the Kreider, again, this is, let's go through it kind of methodically. The Kreider, the Winfield, the upper Fort Riley, and the lower Fort Riley. Well, the Kreider has a layer pressure of 188 psi. The production log shows it is contributing about 60% of the production. Oh, no. The layer depletion from the original shut-in pressure is 59% depleted, okay? About 450 pounds was the original. The flow rate out of here was 564 MCF per day, which was 47% of the total rate producing from that well. The Winfield, 210 psi. That's not a gas gradient. You can't get to that pressure on a gas gradient. Layer depletion about 55%. It's contributing 28%. The upper Fort Riley, 238 pounds. 23% of the total rate, about 48% depleted. And you get down into the lower Fort Riley, now it's only contributing 2%, and layer pressure is 284 pounds. They go in there, they haven't produced any gas from this well at all. They drilled an expendable well, and they go in there and take layer pressures and run some flow meter. So this is the pressure at a point, really. So there could be a gradient into that area. But this is only contributing 2% of the total. This is their low perm layer, and you see The layer pressure here is 284 pounds as compared to 188. So there's 100 pound differential depletion. And again, the original pressure is about 450. Well, they shut the well in then after they ran all these to get a commingled shut-in pressure. You get 190 pounds. You know, this pressure is invisible, that pressure is invisible, that's invisible. This is the only one that it is recording. If you do your material balance on a P over Z and get an original gas in place, what do you have? You're assuming that all these layers are 188 pounds also. You know, so that's where your error is coming in. And you have to see this. You know, at times I wondered when we have run production logs on the EcoFisk wells, or particularly after getting RFTs on wells, have we ever run, taken the opportunity on those wells after that to get a commingled shut-in pressure? It would be interesting if you have any of that type data in your files. You know, to really pinpoint and show what are we getting when we get a shut-in pressure on these wells, where you definitely have the differential depletion. You know, here you can see real, without question, what it is. It's 190 pounds, is just a few pounds higher. Now you got to be careful, because this has probably got a -5 skin, because this is the more permeable layer. You stimulate at the beginning. This is the one that you're going to get the good stimulation. What pressure would you expect if that's a plus 50 skin on this? Now, it's not going to just be only 2 pounds above. You're going to have resistance to flow, the backflow into that layer, so it's going to be higher, okay? So that could be trying to tell you something as a diagnostic tool, too. What would happen if this one were on the bottom and one of these was producing some water and you shut it in? You're injecting water into the reservoir, the best permeable layer, which could lead to some type of skin impairment or damage. Now, if it's EcoFisk, you'd just be water flooding in a sense. You know, be imbibing. But, you know, these are some things that you can start to consider. Some of this phenomenon may explain a lot of things now that you go back, look at data, and say, hey, this ties into some of this layered no crossflow effect. You know, you go and run a production log and you got a negative 2,000 barrels a day, you know one of those layers is taking a fluid, and you know, you clearly have a case of differential depletion. This is the Phillips expendable well that we drilled on our section, buff number 3. We got these pressures by going in, we drilled an expendable well, we did a very light acid, extremely light, just to make sure a few of the perfs were open, and then we went in there with packers to get the layer pressures. The Harrington, I think this was roughly 1989, and again, original pressure over 450 pounds. The Harrington, 314 psi, the Kreider, 121, and the Winfield, 141 psi. But you go on the original well on a section and you get the shut-in pressure of the well from the last official test, and it's around 120 pounds. You know, so that's what we're seeing. If you take a 72-hour shut-in pressure on a well where backflow is occurring in the real world, all you have to do is have the right reservoir model description, and you'll exactly match that pressure too, by shutting in the model. You don't need a buildup or a P-star or P-bar. You exactly match the pressure in the model exactly like it was taken in the field, and that's what we did. You matched it by shutting the well in the model for 72 hours and flowing it for 72 hours to get the official flow rate test. Then when we match the back pressure curve or deliverability curve and the 72-hour pressure, then we have everything matched. The whole material balance and the well deliverability and the well skins And you need these layer pressures, at least one well on your study area, because you have to match this in order to get the volumes right. You have to match the layer pressure. And of course, you are getting RFT pressures from a lot of your wells, so if you're including that in your match, you're actually approaching what we did here. But wouldn't it be a lot easier if you could just shut the model in for a short period of time to match the spot pressure that you're taking? I realize that's a very complicated problem and you might not be able to do it. You got to take a look at it, though. This is an example of a mesa. You see, they drilled 5 expendable wells, and they shut in the original well and started to produce the expendable well, and then took data, had to report the pressure data to the Kansas Commission every month. And I think this went on for about 12 years. This is equivalent to the P over Z versus Cume on the number 1 well, approximately in the center of the section. This is the Mesa Cromwell number 1. And this is the P over Z line, okay? They drilled this expendable well, the A1. That was the original shut-in pressure they got on the well. That's a commingled shut-in pressure. It was higher, but it was only higher, what? Maybe 20 pounds. Now they shut in the original well, and they started producing the other one. Look how it came down on exactly the same trend. And now the original well, because it was shut in, this is the observation shut-in pressure on it. You know, the difference between these two is a gradient, a flowing gradient. You pressure between these 2 wells. You know, but did they add any reserves? You know, they're originally trying to claim that these high shut-in pressures proved they had added additional reserves to these infill wells, or these replacement wells, exactly following the same trend, and it basically represents the pressure in a more permeable layer. And you have to be aware they've drilled over 150 infill wells. Never, ever has any well ever come up to original pressure. Have they ever reported one that come in at 400 pounds or even 300 pounds? When they do, it's a non-reservoir, or it's a non-commercial well. You know, you could drill into an area of extremely low permeability. It just isn't able to drain, and of course you don't have a well. It's a non-commercial well if it's that high in the first place. Very interesting example here. New technology, the advantage of new technology. There was a period back in about '64 where a lot of the companies were going in and re-stimulating or fracking wells out there. This is the original well. A back pressure curve, shut-in pressure squared minus flowing pressure squared versus a flow rate, the 72-hour official deliverability test that were taken annually. All of the points fall on a common line, never changed. So they moved in there and they refracked the well. And that's how much they moved it to the right, okay? A lot of the original wells were kind of commingled, even open hole. We didn't go too much into that. But where you have to come out on this is the replacement well, or the infill well. You stimulated. If they hadn't re-stimulated the original well, what would you have concluded between this is the original well on a section, this is the new well on a section? It presented evidence to prove that infill drilling is good, okay? The new technology of stimulation is going to give you better wells. Yeah, the current, there's some operators, and I think I may have one in here, using big sand fracks, lots of fluids. You can compare those with the original, and they're way out in here. One operator is creaming themselves because they're doing it on every well, and every stinking well is worse than the original well on their infield well because they're using big volume sand fracks. it would be easy to conclude, again, if they hadn't re-stimulated this well, that the infill well is obviously a lot better than the original. It's added new reserves, or the completion techniques are a lot better. It's not. If you'd plot the P over Z on that well with time, or the pressure with time, look what's happening. This is the production curve before the re-stimulation. It cycles because of the seasonal swings. You know, I think every gas field has that. They re-stimulated the well. It's going down. Well, they're producing a higher rate. The 72-hour shutting pressures are after a higher flow rate. They drill the replacement well. The pressure comes, or it starts out higher and it comes on with the very same trend. But notice one thing that they were smart enough to do from all of their studies. The allowable is based on deliverability, which is strongly a function of the level of shut-in pressure, okay? Because the standard deliverability pressure now is getting real close to shut-in pressure, and the further apart you can get it, the higher allowable you will get, and you'll get a bigger portion of the total field production. They suddenly discovered that well, they used it at the very beginning. Do you know what these gaps are between here? They're resting the well. When you rest the well for 3 months, what are you doing? In a layered no crossflow reservoir situation. It may be shut in for 3 months to the surface, but what's it doing at the bottom of the hole? You're injecting gas from the low perm layers into the high perm, and the high perm is giving you the official deliverability, the flow from it, plus the shut-in pressure. Look at the 1 year they failed to rest the well. You know, it is definitely lower than it was before. So at least they did all this work, and they really understood what was going on, and they used it to their advantage, yet to increase their allowables. You shut into the surface, you're flowing downhole, and they'd rest them about 90 days. And they'd take their allowable for the remaining year a different time. But they were able to increase their allowables by using this. The idea, you're resting, and then you can see if they didn't rest, what happened. We've talked earlier quite a bit about the Q max over the G sub I ratio, and again, we'll get into it. That's the potential of the more permeable layer over its gas in place, and the potential less permeable layer over its gas in place. That gives us the ratio. If you substitute in terms of reservoir variables, it turns out that is nothing more than a ratio of dimensionless times, if you're used to that type of terminology in pressure transient analysis. The only difference is this is for a finite system, not an infinite system. You know, the dimensionless time that you're used to dealing with is for pressure transient is for an infinite system. The only control you have over this ratio, decreasing the differential depletion. Remember, it's this ratio that gives you the spread on the differential depletion on a P over Z curve. As the number gets larger, you get more differential depletion. The only control you have to shrink that number, to make it smaller, is the skin on a low perm layer. That's the only control you've got. You know, you can drill an infill well, and I'll probably cover that in another slide. If I multiply this by 2 and this by 2, it cancels. Differential depletion stays the same no matter what I do, how many infill wells I drill. So the only thing I can do is to get the largest negative skin I can on the low perm layer at the beginning, very beginning, you know, because these wells aren't going to last forever. If I don't get it early, it's going out the end. You're going to leave it behind. This is a good place. All else being equal, on a Q max over G sub I, I can have equal permeabilities. You know, even if I put a KH and a pH, the H's will cancel. So I can have equal permeabilities and thicknesses and porosities and skins, and it comes out I can have a Q max over G sub I ratio exclusively controlled by volume. So I don't have to have a permeability ratio to see differential depletion. And they're work through just a real small exercise tomorrow to kind of demonstrate that with a 2,000-foot radius on with this layer and about a 700 on this layer, I've got a 10-to-1 ratio. Yeah, so be very careful of thinking, if I don't have the permeability contrast, I'm not going to have differential depletion type behavior. There's a copy of a paper, layered no crossflow, or what is the title of the paper, the first one we published? Depletion Performance of Layered No Crossflow Reservoirs is in your book. A lot of these equations are in there, an example. So you don't have to worry, other than you ought to take some of the, maybe the keynotes along the way to kind of remind you what to look at. But, you know, the conventional material balance for one layer is this, P over Z. You know, you can derive it 1 minus GP over G sub I. For two layers, though, we have a different system. We have the cumulative production from both layers. You don't have to confine only to two layers, again, but it's easier to talk and understand concepts. I keep it simple. And, of course, when you're measuring at the surface, you're getting both, and you have no idea what the split is. And, of course, the gas in place has got to be the gas in place of both. So that's only this entire system would give you a straight line, if you can get all of this information plus those two separately. Yeah, so there is a little difference in a P over Z equation for a multi-layer system than it is for a single. And that's why you end up with a curvature. And that's, you know, that's what this figure is trying to demonstrate. A volume ratio 1-to-1, you know, so that this you have a straight line down here to the gas in place, the more permeable layer. This would be the gas in place and less permeable layer. The line pressure, it's asymptotically going to approach the line pressure. It's going to get flat. You know, so it gets back to, you can actually see data in this region as the shut-in pressure, the more permeable layer approaches that line pressure. The higher permeability, you know, it's going to get there quick when you drop the line pressure. Real quick, it'll go up and then come down and approach that. Basic thing to recognize, well, you can see here that regardless of what skins, as long as the skins are equal on all layers, no matter what we run, we get the same identical P over Z. The Q max over G sub I ratio is always the same. You know, this represents P over Z for the total system. And the distance between the total system and the more permeable layer and the less permeable layer is always in proportion to the volume ratio. It's a little tool that you can use to kind of estimate, maybe from the shape, because you can draw this. If the less permeable layer were, you can draw this envelope from a horizontal line from the initial pressure over to the position where this represents the more permeable layer. Well, that's the upper limit of the envelope. Well, this is the lower limit of the envelope for the more permeable. So I can sketch something in between. If this is real high perm layer, it's going to come down like this, and if this is low perm, it isn't going to produce anything. You know, so it's going to be a horizontal line, and then I'm going to drop down after this one's depleted. The only production I can get is out of the high perm layer. The same concept. Let's remember what this represents. There's a copy of a paper that I think you're going to get where Shell went to the commission, the Railroad Commission, and said, we have these stacked reservoirs like in the Gulf Coast. They may have several different reservoirs. Now, how do you want to produce it? It's just like a layered no cross flow system. Oh, okay. Some people are colorblind. Don Ebbs is, I know, you can't use red with him. One, two, three, four. You know, there's a lot of these type reservoirs in the Gulf Coast. I think there's a lot of these type in Nigeria, where there's no question it's layered no crossflow because they're separated quite a bit. But what strategy would you use to produce these layers with time? Well, what a lot of people have done in the past, they start at the bottom, produce those, and produce it to its economic limit, and then they keep moving up. Well, you could take this Qmax over your G sub I ratio, and let's just you change it to one thing. And let's just add an N in there for number of wells, so that if we had one well in there, you know, I got a Qmax over G sub I, no problem. What if I what would I add if, let's say at the beginning, I'm going to complete, I'm going to commingle these two. What would I do for these two layers while I'm drawing a P over Z versus cum for this entire system? Well, these two layers are going to be zero. You know, I have a zero well. You know, so I'm going to draw a horizontal line on the P over Z for the total system. I can actually generate a total P over Z for this whole system. One of the things that comes out of layered no crossflow reservoirs is long producing times. Okay, this is exactly what you're going to have with this type system here. It may take you 50, 75, or 100 years to finally deplete all of these sands. There's a paper in there by Shell about how they went to the Railroad Commission and they doubled the production from their gas field. It's the McAllen Ranch. By convincing them the optimum way to produce these type reservoirs is to commingle it. And that gets back like the skin on a more permeable layer. You can represent the same thing. Instead of a zero number of wells, you can say I got a skin of 1,000 because I never perforated that layer. Okay? Well, you're going to leave those reserves out of the end because the life of the well may not last that long. So these types of systems, if you sequentially come up, you're imposing a real long producing life on the wellbore. So the optimum way of really producing it would be to commingle it. But when you start getting in the Gulf Coast and other areas, you have to be careful, you know, because some of the high perm layers may develop water influx, water drive, you know, strong water drive. So just something to keep in mind that by the same logic, you can read that paper and you can start thinking it. If you're going all through this and you recognize that a layered no crossflow system results in long producing times, that's exactly what this type of system does too. Because you're not perforating all the layers at the same time. You're not commingling at T equals 0, which is what you should do to recover the maximum amount of reserves. This is the type of configuration that we have for with a red cave, twice as much in the low perm layer as the high perm layer. And you could take these figures and a pair of dividers and go and measure, and you'll see the distance between the total system, straight line P over Z, and the more permeable layer is exactly 2 to 1. But this represents the volume of the low perm layer. And it's almost intuitive. the smaller the volume of the high perm layer, the quicker the pressure is going to drop off the end of the table. So you're going to get that type of curvature. And again, you can bound this figure by drawing a straight line from the initial pressure to the volume of the with a more permeable layer, and from here to here is the less perm, and you can draw the horizontal line and this line, and you've bound what this is going to look like, what it should look, and you can sketch it in. And very roughly, like I said earlier, the tangent to this thing is approximately pointing to the gas in place of the more permeable layer. There's a rule or an observation that a lot of people have made with water influx in gas reservoirs, that because of the delay in the water moving into the reservoir, if you take that early pressure cum data, it will approximately extrapolate the original gas in place. That's for a single layer system. Well, you have a similar type logic here, that those early shut-in pressures are trying to point in the direction of, you can at least get an idea, is it small or big? The smaller the low perm layer, or the high perm layer is, the more precipitous the pressure drop is going to be. And it could look like a very highly undersaturated reservoir too, because the pressure is dropping. So a precipitous drop in pressure is a characteristic of the shut-in pressure of a layered no-cross-flow reservoir. I think I may have already shown this before, but this is kind of a little better since each of the lines are differentiated. This, as the Q max over the G sub I ratio approaches a large number, this approaches the envelope that we were talking about. And as it approaches 1, then this is going to approach a straight line. And the distance between these amounts to the differential depletion that you should expect to see. Like here, you get 100 pounds in the more permeable layer here. The less permeable layer is going to have about 370 pounds reservoir pressure. And again, you can see how you've got hidden reserves that nobody knows is there because you're not getting that pressure. There's no way that you can detect it, except you have to spend the time and effort to go in and get RFTs or layer pressures. Now, even there you have to be careful. I showed you earlier something very similar to this. One case we ran is a constant rate and the other constant wellbore pressure. It's in the original paper that you should have in there. Again, the 72-hour shut-in pressures, how they have a tendency to be closer to the high perm layer, and the pressure is dropping off the end of the table. And again, this is for a 2-to-1. You've got twice as much volume in the low perm layer than you do the high perm layer. Now, interestingly enough, it is this example, what it's trying to tell you is that the potential of rate sensitivity in a layered no cross-flow system. As Q approaches 0, which is, of course, a ridiculous assumption other than to recognize that it is potential rate sensitive, everything else in this entire system is the same. If you're to produce the well at 175 MCF per day or 300 MCF per day, the volumetric average pressure in each layer is going to be exactly the same, independent of these two rates. But as you approach 0, you start shrinking the differential depletion in layers. As Q approaches 0, they'll both deplete equally, but it may take 1,000,000 years to produce it, of course. But we're just trying to introduce the idea that it can be rate sensitive, the amount of differential depletion that you see. All I'm trying to do here, again, I think we discussed it before, is these very simple equations demonstrate very clearly that infill drilling in a layered no cross-flow reservoir will add no additional reserves, because the Q max over G sub I with 1 well, 2 wells, 3 wells is the same. You cannot change the amount of differential depletion occurring within the layered no crossflow reservoir by infill drilling, by adding an additional well or two or three. It's really important to understand that, because that's real hard to accept as logical. I understand that. It just doesn't make sense. But this real simple equation tells you why. That ratio determines how much differential depletion, and whether I've got 1, 2, or 3 wells, I can't change that ratio. But like I mentioned before, I can change it by that skin on a low perm layer, which is adding additional reserves. And you got to do it early. You'll see in some of those papers where Shell and that water flooding paper, which is a classic on layered reservoirs, and they show the differential depletion, but they don't recognize it as such, but they clearly demonstrate all the original wells were open hole, thick carbonate, and they tried to get the diversion. It was water flood to get more equal distribution and everything. And they tried balls, and it didn't work. They mechanically had to do it with packers. Or, in our case, all our original wells in the Oklahoma Hugoton were with, in Texas Hugoton, were with bridge plugs in between each. We separately stimulated each. There's another paper in there, too, you'll see on, it's out of the Oil and Gas Journal on a reef reservoir in Illinois. Same identical observation by trial and error. It's layered, no cross flow, and they tried to use the ball sealers to get the diversion. Didn't work. They had to do it mechanically. And they attributed it to all kinds of things, teamwork, this, that, or the other. They never once recognized it. It's layered, no cross flow. It's actually getting the increase. You know, we're going to, with the very, very, very simple equation, we're going to go through and try and demonstrate how you're going to calculate the calculation of times and the economic rate of 10 MCF per day. Each layer is first as if it's produced separately in wide open. Again, we're just going to look at these equations, see what it's going to result in. And we're going to assume the commingled well production is going to be wide open. Again, each layer is going to have the same PWF. And we're going to use this equation here. So the time to an economic limit is just rearranging this equation and substituting in an abandonment rate. I should have got into this early. How do you talk about abandonment pressure in a multi-layer system? You know, you saw the P over Z's. What is it? What does it represent? Well, nothing. I don't even know how to get there from here. You see the total system P bar, each layer. Let's go back to that just for a second. You know, how would you discuss abandonment pressure? Is it this pressure? Is it this pressure? Is it that pressure? Is it this pressure? How do you get it? What does it mean? It may mean something with regard to a single layer system, but what does it mean on a multi-layer system? It means absolutely nothing. You know, this is everything's approaching this anyway, so whatever line pressure I'm going to set is going to look like an abandonment. So you really can't talk about abandonment pressure in layered no cross flow system because it don't make sense. You don't know what to talk about. But abandonment rate or some economic rate, that makes a lot more sense. And that's how we ended up really doing our work with regard to the model, was get to look at abandonment rate. And all we're doing here is rearranging this equation and substitute in for QGT an abandonment rate, and we checked with the field, and 10 MCF per day is the current one. So we're going to use that, and we're going to calculate how long it's going to take for us to get to an abandonment rate of 10 MCF per day for each layer individually. And then we're going to do it commingled. And see what evolves out of that. Well, the only reason I'm going to introduce this is, okay, now what are we going to do for a multi-layer system? Instead of one layer by itself, and it's just a summation, really, of each of these individual layers, to where the sum of all layers is going to equal 10. If 10 is the abandonment rate. This table is in one of the papers, I think, on the 5 papers that we had published on the Oklahoma Hugoton. We need to spend a little bit of time with this, okay? Here's the permeability of the herring. This is for the Buff 1 well. That's the one where we had the layer pressures, and it was a key well in our study, so we just took its parameters. Harrington's got about 1/10 of a millidarcy, the Kreider 9, and the Winfield 3. Your thickness, 58 feet, 50, and 40. The thicknesses are very close to being the same. The KH, and here we got your 6 millidarcy, 452, 131. The skin minus 5. Has everybody found that page? Why don't you, somebody that's on it, why don't you tell them what page it's on? There's a top number or something like that.
36.
Is everybody there? Sometime when these things are put together, some pages disappear in some of the manuals. Okay, does everybody have it? All right. Yeah, so this is Qmax. This, let's give it some kind of physical meaning. This is the absolute open flow potential of the Harrington layer. This is the absolute open flow potential of the Kreider. Like if you plot a back pressure curve, but you got a slope of 1. And this is the absolute open flow potential of the Winfield. And this would be the sum of those. That if I was to take this same problem and I'd say, well, what would the rate time look like if I have some cross flow? Well, I just sum up all the Qmaxes, and that's going to be my initial rate. And I'd sum up all the gas in place, and that's going to be my gas in place, and I'd assign a B value of 0.4. That's what you assign for a single layer system. Then I make a forecast with cross flow, which would be that one, or no cross flow, which is the other one. And then I can compare the rates. You can do it on the back of an envelope. How much difference are going to make for these given set of variables. But here we're just primarily going to talk about the time to abandonment rate, okay? So this is the gas in place of each of the layers, and this is the Qmax over G sub I. And as you can see, the more permeable one is the highest number. Okay, and this is the ratio. We're going to reference the ratio now in more than 2 layers, always to this larger number. So this is 1. All right, this is 1.76. This ain't bad. I mean, they're very close to each other. And this is a big difference. This is 50. So this is going to be the low perm layer. And to 10 MCF per day for the Harrington is going to take 78 years to get, if I put it on production, wide open, it's going to take 78 years to get down to 10 MCF per day. Kreider is going to take 24 years. That's a normal time span for the depletion of a field, or a layer, okay? The Winfield is going to be 21. It's going to take 21 years. If I throw away the Harrington, heck, I'm going to deplete this field in about 23 or 24 years, aren't I? But because, which gets back to the idea, the low perm layer is gravy. You should not be forced by anybody, by governments or what have you, to say, you got to spend all the money in the world to go after this one too. That's a plus. It should never end up to be a negative or a minus. Say, well, look at the high pressure in there. You're banding at 211 pounds. You should do something. In the layered no cross-flow system, you can't do nothing about it. So the fraction recovery at this time would be 54%, even if you'd abandon it in 78 years to its economic rate. You only recovered 50%. But in the crater, you would recover 95%. In the wind field, you'd recover 90%. But if I calculate now the time to an abandonment rate of 10 MCF per day for the commingled well, it's going to take 89 years. I've gone from 24 years from the crater and the wind field. Now the whole system to 10 MCF per day is 89 years. The tail's wagging the dog. The low perm layer is what's kind of setting. But this gets back. Layered no cross-flow reservoirs that have this contrast are going to have long lives, 89 years, at the abandonment rate of 10 MCF per day. But look what's contributing. At that time in 89 years, I'm getting almost all the production out of the low perm layer. 8.5 MCF per day. I'm only getting about 8/10 out of the crater, 7/10 out of the wind. But there's my 10 MCF per day. That's my abandonment rate. This is why you look at these problems in terms of abandonment rate. There is no such thing. And at the time of abandonment, 10 MCF per day for the commingled well, I'm still only going to recover 57, 98, 97. But look, I'm going to leave 211 pounds in there. You go through the same exercise and multiply this by 2, 2, 2, and go through. You end up the same place. You shorten the time. You can shorten the time. But the pressure that you abandon the system, that's identical. And I think we have some example. I don't know if it's the next overhead. It'll come later. I'll show you, though. We're going to use this very simple equation for the model. Using the model gas in place and just summing up each individual well's absolute open flow potential, and we can calculate within a year the abandonment times for each of the layers and the abandonment rates for the 12-section model study. With this very simple equation, you're running the model for 120 years. So you're just trying to get you to realize that you can analyze layered no cross-flow reservoir behavior very simply by using these very simple rate time equations. And regardless, even though you'll see in those calculations, even though I'm using PWF as 0 and all kinds of simplifying sums, and I'm very rigorous in the model, I get the same answer. That's the whole point. One of the exercises we're going to go through tomorrow is we're going to calculate a production forecast with the hand calculations, and then I'll give you the numbers with 7151 and numbers with the model, and there's no difference. There's no engineering difference. Okay?
On this commingle that you have there, after, let's say, 23 years, do you expect the recoveries to be just about as on the left side there?
Yeah, you can see here that we really haven't added that much more by going from 24 years to 89 years to the two good layers. Okay?
If you commingle after 23 years, it would be opposite.
No, this is all commingled. I just did this to demonstrate if I produce them separately to 10 MCF per day. Remember, when you're producing a constant wellbore pressure, they're totally independent of each other. It has nothing to do whether you're commingled in a tubing or not. Okay? Absolutely nothing. Just trying to demonstrate each one individual. If I had each layer by itself, what would it do? To 10 MCF per day. How long would it last? I tried to point this out earlier. You've got to really think. Don't confuse yourself with thinking if you have separate completions, you're going to change anything. You're not. Because each layer always has the same flowing pressure, exactly at the same time. It's hard to get over this concept.
I think his question was that if you had cross-flow, would it then look like it is without...
No, I didn't interpret it that way, because I've got this question all the time. Is if I had separate tubing strings for each layer, would it make any difference? No, it doesn't change anything. Now, other than you'd never develop this one, it would never be commercial. That's where you're heading. You'd never develop that one. That's what I meant when I said this is gravy. You know, I'm going to produce these anyway. I'm just adding this on as gravy. It should never be considered a negative. When I say separately, that was only to do a calculation to see how long it would last to a 10 MCF per day separately, okay? Not that I separated them out in the tubing string. The flowing pressure is the same for both. They're totally independent of each other. One does not inhibit the other at any time. If you were producing at a constant rate, it would, okay? That's why it's really nice to look at this whole problem. So you get real bogged down when you start looking at everything as a constant rate. I can't make it any clearer than you present it in terms of a constant wellbore pressure. We'd have never solved the problem if we were faced with, if we hadn't got into the red K first, because when we get into the Guyman-Hugon, it is a constant rate case. What ends up happening, like I mentioned earlier, when we go on decline, is the volume ratios that I would have had at the beginning have changed when I start on decline, so my decline exponent is going to be different because I produced at a constant rate. And we'll even show you with the model, if I had produced the field wide open from the beginning, it doesn't change the long time. It's still a long time because it's layered no cross flow. There's a lot of new content. I know that this has got to be overwhelming in terms of trying to give all these concepts at once. But again, we're talking about them. You know, everybody's being introduced at the same time. You can talk to each other. You can go away later. All this stuff is in that book. And if you read and understand it all, you're going to have 38 years of experience. You know, I said that earlier kind of as a joke, but it's not entirely a joke. This is a real hard, you know, just like it's almost incredible to think in terms of you can drill an infill well, layered no cross flow reservoir, and you don't get any more reserves. It just doesn't make sense. You can run the problem forever on a model, okay? But when you reduce it to these very simple equations, you see exactly why this is true and exactly why that. And then run them all, you find out, by golly, I'm getting the same thing. And you know, this is a part of the reason I think nobody really is grabbing onto this concept, because it is difficult. And you have to work through some problems. You have to be involved, because you'd never sit back in your chair and dream this up, this type of situation up. You have to solve a problem, and then all of a sudden things start working. And we were lucky for, like I said earlier, two reasons. We're working with single-phase gas to keep it clean. This is always an advantage. And then we were working with a reservoir that was producing virtually wide open from the beginning, and we were working with rate time data. You know, and that's the only way you can get a B-value. We started talking earlier about ARFs. You can't get a B-value in excess of 0.5 for any analytic type of system you could dream up for a single-layer system. It does not exist beyond the 0.5, and you have to get into the layered no cross flow, or its equivalent, the composite. Remember, I tried to take the layer and turn it over. I can have a regional. It's going to give me the same type of logic that I have to follow. If I wanted the two fault blocks, which would be sealing to deplete at the same, I have the ratio Q max over G sub I. If the geologists give me the gas in place of each fault block, and I have an average well, and then I can calculate very quickly how many wells I have to have in each fault block for the pressure to deplete equally. Or there's a little exercise here I think we'll go through later. If I wanted the Harrington to deplete exactly the same as the Kreider, how many wells would I have to drill? Well, I've got the Q max over G sub I, and I put in number of wells, and it turns out I'd have to drill 29 wells in Harrington for the pressure to come down to these same two values when we deplete it, while I have only one well in the Kreider and the Winfield. I can't afford to spend that kind of money. Somebody should not force me to make the pressures equal. That's what would it take. 29 additional wells to be drilled in Harrington to come out with the same abandonment pressure all along the line in time.
This type layer, would it have been considered there to use horizontal wells?
The easy, good substitute, earlier in our session, use a -7 skin, see what you get. It's not going to be much better than a -5, is it?
Well, it'd be about $1 million then, wouldn't it?
Like I said, you have the equation, just work through and put a -7 instead of a -5. You can calculate how it would change any of these numbers. And -5 is a very good skin, and we're going to get through that here. I'll show you the values that we got from these original tests. We were fantastic. In 1945, we got -5.5 skins on all these wells. We ran pressure buildups on some of these wells in the study area in 1989. Guess what? Same skins as they were in 1945.
Do you ever consider infill drilling due to you just drain 54% of the low perm layer after 78 years, since it's relatively high paid?
Well, we're back to the same place. We've answered this question earlier. The infill drilling isn't going to change it.
No, I see that. But
Okay.
the time to reach pseudo-steady state.
Oh, it don't make any difference.
For low perm layer.
Well, the time to reach pseudo-steady state in this layer is about 3 years. In this layer, it's about 3 months. The difference in answers that you get, including or excluding transient, it doesn't change it. You can't plot the difference, okay? Because its rate is so small compared to these other rates. It's a good question.
Okay, so
Because I heard the question raised at a school or seminar that was given here before, and that was being misinterpreted. I already looked at that in the model. It doesn't make any difference.
so how low perm would you ever consider doing infill drilling in a gas reservoir?
Now, if you take this along as a separate thing and you remove it from this as a separate thing, you might look at it differently, okay? If I don't have an economical well by infill drilling and just accelerating, including the Crider and Winfield, ain't no way I'm going to get an economic well by completing only in the Crider, see? We ran the economics for drilling an infill well on every one of these sections in the model and completed in all 3 layers. It is not economical. If it's not economical, at the stage that we're at where these are producing the majority, it sure isn't going to be. We even looked at the effect. Well, how much more would it produce? Because if we complete it only in here, because the shedding pressure is going to be so high, we'll get a higher deliverability. We don't even pass the transient, and we're already below the calculated increase in allowable that we thought we might gain. Like I said, there's a lot of things in this real little example. That's a very good question about a horizontal well. Again, put a -7 in there. RW prime is equal to half the drill length of the horizontal well divided by 2. Put a 4,000-foot horizontal well in the problem and go substitute the skin. And that's even saying that you have 0 damage as a result of the drilling. It's a pure, good -7, -8 skin even. Run through the exercise. It's real easy to do. What would you do? How do you drill a horizontal well? Because it was raised in this entire issue at one standpoint. If you drill a horizontal well, where would you drill it? Would you drill it in the Harrington layer only? Well, you're not going to get any more production out of the Crider and the Winfield if you only locate it there. And then, well, but let's drill an incline well. Once you drill an incline well, look at the maximum deviation of an incline well through all 3 layers. It's about a -3.5 skin. You're no longer getting skins of horizontal wells. It's I think Standing has this figure in his book up there at Trondheim of the effect. If it's not in there, I know that Ramey had it. Of an angle theta of a slant well through each layer, and say, well, that's equivalent. The most you can get is about a -3.5 skin. with a high angle well through each layer, in each layer. You don't get a -7 out of it. You can only get that by confining it to a single layer. And then that well won't drain the other layers. See, this is something that ought to really be considered when you're drilling horizontal wells. Is this a layered no cross-flow reservoir? And if you locate it only in one layer, the other ones are never going to see it. You say, yeah, but this is unique to Kansas. I'm saying it's not. When you start reading the literature and looking at layer pressures and differential depletion, it's the rule, it isn't the exception. And I followed the horizontal literature quite a while, and the French were the ones that were really pushing all of this early, and they started wondering why. There's a paper that they published that they finally admitted why their calculated increases that they were expecting on some of these projects, they weren't getting them because they had layered no cross-flow reservoirs. You know, you locate that horizontal well, in that layer, these two layers don't even know it exists. Okay? That was a good question. I think it was appropriate because it really belongs in the layered no cross-flow reservoir discussions. But if you have that, you better be very careful where you locate that well, in which layer. And you can calculate it. Again, like I said, put a -7, -8 skin on that. You see what it'll do. You see how much more. That's all you got to do is substitute one number and get the radial flow equation to calculate that. You might be able to do it by ratioing, you know, approximately. What would you think that would increase the number to? Your 49, it wouldn't double it at all, would it? Or the 47? Well, either way, you can do it. A part of our study was to look at the history within the Oklahoma Hugoton of replacement wells. And on here you'll see where we looked. We did a lot of work, you know, to try and solve the problem, what was going on. Our study area, the 12-section study area is here, outlined in blue. We have a little bit of a blue section here where we drilled a replacement well, because the original well was wet, and a lot of replacement wells were really completed mainly because of a deep test down to the marrow. You know, so it was dry, and you came up and said, well, let's see if we can make a better well in the chase formation, and that's what happened here. And a lot of these are probably that, where deeper tests were drilled and we came up and see if we could make a better well. You can see they're scattered all over the field. This region up here is mobile territory. City service, I think they're out in this region. Phillips is down here. We're going to look at 5 replacement well performances. Well, the mobile area where they had not too far north, they did their model study in Kansas, but we're going to look at that, and then we're going to look on the east side, which, you know, you start going down into the water, so you start losing some of the good pay, and you get into ratty portion here, and over here the clastics start coming in, and you get ratty there. And when we had to answer a technical questionnaire by the Oklahoma Corporation Commission about if we're going to do a study, this, that, or the other thing, and is there any potential for additional reserves from infill drilling, we said no, and we quantified a number approximately before we did any work, and then we said if we get any, we would expect it out here on the flanks. Either this flank here, primarily here because they got more clastic, less here because even the good pay is starting to go down into water, and all you're going to be left out here is the Harrington on top, which is going to be above water, but isn't a good reservoir anyway. So we're going to start up north. Well, no, this is the Phillips well on the Strat, okay? Our study area, there was a replacement well drilled. You may not have this in there, or if it's in there, it may be somewhere else, but that's beside the point. You'll see this was the original pressure versus cume on the original well number 1. This is the replacement well drilled practically 2,000 feet away on the same section. And as you can see, the pressure cume, it didn't even change a pound. And so obviously this is in real good communication with that. And that's a pressure cume. So this is kind of reflecting the in-place and, again, primarily more permeable layer. In this area, we just have the Harrington and a Kreider, so it's primarily the Kreider. And we had to put a pumping jack on the well, really. It wasn't any drier than the original well. So there was a pumping jack on there to pump water, and that's the result of the increase. So we increased from here to here, but primarily due to pumping jack. When you plot the deliverability on the well as compared to the original performance back pressure curve, you'll use this as a performance measure. You can see here there are a couple official tests run that were way off to the left of the curve, and we got a poor test, and our allowable probably suffered because we got a poor test. Once we put the pump jack on, this is a new well at a different location that was stimulated. It must have about the same identical KH and skin over 2,000 feet away. Okay, that's the conclusion that you draw from this. We didn't add any additional reserves. We got the same pressure. All right, let's look at the mobile well, and this is up to the north. This is almost into Kansas territory. That's about as far away as you can get from our stuff, but also close enough to what they were doing in Kansas. And you're trying to point out here, this is the period that the gas production in the States was curtailed. You can see the curtailment. Again, in our model, during the period that they reduced the rate, we had backflow going on between layers within the model even because of the cutback, or the increase in back pressure. This is the original well up there. This is the replacement. Some wells were replaced because of casing leaks too. There was a Glorietta, which is real salty, up maybe about 1,000 feet. That we got a lot of holes in the casing that way. But you can see the POZ versus cume. Initially, there was a little bit of rise because of the gradient. Within a very short time, it was right on the same curve. Okay, so no increase in indicated original gas in place. We have a sketch out here showing how the wells were completed. You know, this is the Harrington, Kreider, Winfield. This may even be lower, and here I think we only completed within the Kreider, or Mobile did. And I can tell you all those wells were open hole, and we thought we had a bird nest on the ground. That we were going to go in there and offer to buy those wells from them based on the assumption they were going to do the evaluation on this P over Z and their deliverability. And we did all, you did the legwork and the groundwork. Was ready to go to management. Decided to update the study because it was about 8 or 9 months old. Went in, and they discovered that if they go back to these original wells, they were all completed open hole. Commingle stimulation, they were able to increase the deliverability 4, 5, and 10-fold. And we'd already figured out that this potential open hole completions, you commingle stimulation, you got a bird nest on the ground with a layered no crossflow reservoir to stimulate the low perm layers. And they figured it out. The number 2 well was slightly better than the original well. The back pressure curve, your point shifted slightly to the right, but again, nothing dramatic. It's what you'd expect, no indication. The city service, Tenneco, Enns, Wallace, Enns number 1. It's one of those wells that was drilled. This is the original, replacement 1, replacement 2, this is the P over Z, between 1950 or 68 roughly, and 1981 there was no production. They tried an infill well here. It wasn't commercial. They just abandoned it. They put this on, you know, that's 30 MCF per day. That's not a very commercial well. And there's the deliverabilities always coming out about the same deliverabilities, but between 1967 and 1981, without any production coming from the lease, the pressure dropped from roughly 300 pounds to about 170 pounds. You don't have a commercial well. Rock quality poor, just like you might draw there, you know, draw these pods and so on and so forth. But what happened when there wasn't any production from the section? Oh, it was being drained. There's no pods. You know, this is a real dramatic example. They tried different completion. You could make a commercial well. That's on well, I don't have them identified, but I think that's on the west side, the city service side. With the same thing, the Panhandle Eastern Fletcher, which is on the east side, or the reservoir. Well, this is even more dramatic. You know, there's the first well. You know, the second well in blue was drilled. You know, the first well wasn't commercial back in about 1956. The next well was drilled in about 74, and then finally somebody tried again. That's 100 MCF per month. Okay, divided by your 30, what are you going to get? Possibly the farmer was using this for irrigation gas, or maybe to heat his house, or his outhouse. You know, there probably wasn't even enough gas for that. But you know, between 1956 and 1983, shedding pressure declined on this well from 360 pounds to about 120 pounds. And you don't have a commercial well. Is it being drained? Is there any additional reserves due to infill drilling? Are there pods out there? There's obviously a big change in the quality of the rock, but does that mean there's additional reserves due to infill drilling? And you know, that's one of the problems with that type of a cross-section in highlighting in color the poor quality rock and the better quality rock. It almost implies like you go drill, you're going to find these pods, you're going to get additional reserve. Well, here's a pod. And this is a well in the center. The Panhandle Eastern Burris is roughly in the center. And as you can see, there's the original well, a replacement well. The fact it's so close, it was probably one of two things, either a casing leak or they drilled a deep test and it was dry and they decided maybe to see if they could make a better completion. You know, and then they drilled another well which is a lot further away. I guess this is the final one. And as you can see, there's no difference. There's really no difference in production rate. No real difference in PO over Z versus cum. They all, these three wells are basically following the same trend, and the well deliverability is the same. No improvement resulting replacement wells or so on and so forth. All right, now I'm going to take you. I got one here that I'd like to show you. You know, everything that we've learned. We looked at 30 of these wells. They're down in the Texas Hugoton. I'll show you later. Because we were operator down there in Texas Hugoton, we were taking our gas out a lot faster out of Texas Hugoton than people were out of Oklahoma, or the people in Oklahoma were taking out faster than out of Kansas. So the Texas Hugoton went on decline. The wells went on decline back in '73. Even earlier. So we had a period that we could look now after we understand what's going on. Purely rate time data out of the Texas Hugoton without doing any more studies or what have you. We looked at your 30 sections down about 7 miles south into the Texas Hugoton. You can see This is out of Dwight, so we don't have all the data. We could have gone to our files and supplemented, but you could see the curvature in the P over Z. The deliverability isn't that much difference, and you can see a B value in the rate time of about 1. It's an expected value decline exponent at this stage of depletion that we should be expecting to see in the Texas Hugoton. So we know it's layered no cross flow too, just like Oklahoma and just like Kansas. It's the same formation. It just extends for literally hundreds of miles, layered no cross flow, hundreds of miles. Not a few miles, but hundreds of miles. Now, I'll start with the end before I get started at the beginning. Now, these are the conclusions that we drew out of the work we did for the Oklahoma Hugoton, and then you take a break and get back again after lunch. The following observations have been made from Phillips Reservoir Simulation Studies of the Oklahoma Hugoton Field, and these may or may not be in a paper. Again, we've got 5 papers. First, a single well reservoir simulation model study cannot realistically be used to evaluate the infill drilling potential in the Oklahoma Hugoton Field. A multi-well reservoir simulation study is required because of drainage effects from offset wells. Well, normally, if you had a single layer, you could look at the offset wells and say, well, if I proportion the rates between these wells, I could set no-flow boundaries, and I can run a model, and I can draw some conclusion. I got 3 layers, and I don't know what the rates are in any of the 3 layers. So I can't proportion R sub E's in each of the layers. So I can't solve the problem on an individual well basis. To realistically predict the future performance and production from infill wells, a multi-well, multi-layer simulation study must be used to reasonably history match the following historical performance of reservoir data. And this is what we're going to go through this afternoon. Each well's official test, the shut-in pressure, and the cumulative production data, the P over Z versus cumulative production. Each well's official 72-hour deliverability, and of course that's going to lock us in on a KH and skin. The Harrington, Kreider, and Winfield layer pressures in at least 1 well in a multi-well study. You can get, it's a classic example where you say, well, I get a match, but it isn't unique. When you match those layer pressures, you've now made it unique. You can't get any other match but that. Without the layer pressures, I could get a big range of values. And I'll match the deliverability and the P over Z versus Q. But once I have to match the layer pressures, then there's only a single answer. And so this starts to get into the uniqueness of a solution with a model. You give me the layer pressures and it's unique if I match the layer pressures. And then the other thing we had to do there is how close could we come to matching the replacement well on that Strat lease that was located about 2,000 miles away from the original. If we can do that, that's equivalent to drilling an infill well. What we ended up doing really was we didn't change a single number of the KH distribution that we had for each layer from the original description. We used the same skin there as the original well, got a perfect match without turning a knob on a replacement well on the Strat. So we figured we got it locked now. We had a unique match and we matched everything. And we'll get into the details this afternoon of the details of the model study. Any questions at this point?